How's it going? So in this video, we're going to be going through a system of differential equations example where we're given the system dy dt is equal to 5y plus 2z and dz dt equals 2y plus 5z. Okay, so we're going to have to use some linear algebra here. And the first step is going to be to assemble a coefficient matrix, and that's just defined as the rows taking up the coefficients of each of the equations. So we got a 5 and a 2 here, so we're going to throw a 5 and a 2 in our first row, then we're going to have a 2 and a 5 in our second row. Okay. Next step is to calculate the eigenvalues and eigenvectors for the specific matrix. If you're unfamiliar what those are or why we need to calculate those, I'll go through that briefly. Basically, because we know that this is a constant coefficient matrix, we know that solutions then, similarly to when you had higher order single differential equations, solutions are going to be exponential, 1, and 2, they're going to take the form, we'll call this vector valued function g of t, they're going to take the form c1, right, a constant times eigenvector 1, I'll call that x1, times e to the eigenvalue 1 t plus c2 x2 e to the eigenvalue 2 times t, where our lambdas are our eigenvalues and each x with the subscript is the corresponding eigenvector. And so essentially an eigenvector is a vector that when multiplied by a matrix A, right, so we have a vector x, when it's multiplied by a matrix A, it remains on the same direction, right? It keeps its same direction, and it's simply scaled by a factor lambda, right? So what this equation tells us is that when we take a vector and we multiply it by a matrix A, that's going to be our coefficient matrix, we get a vector that is in the same direction as our original vector, except it is scaled by a factor of lambda, right? So that's important. That's very important. And so from that, we get that the determinant of a minus lambda I must equal 0. So to do this, we're just going to subtract lambda across the main diagonal of our coefficient matrix. So we're going to have 5 minus lambda, 2, 2, and 5 minus lambda. Just subtracting lambda across this main diagonal because this is multiplied by the identity matrix I. And so that's equal to 0. So from this, we got 25 minus 10 lambda plus lambda squared minus 4 is equal to 0. We can easily factor this as negative 7 and negative 3. So our first eigenvalue is equal to 7, and our second is equal to 3. So those are going to be important. And now I'll go ahead and calculate the corresponding eigenvectors for each eigenvalue that we just found. So for lambda 1 equals 7, we know that a minus 7i times our first eigenvector, x1, is equal to the 0 vector. Okay? So by that, we're just going to subtract 7 across the main diagonal of the original coefficient matrix up here that we called A. So we're going to have negative 2, 2, 2, and negative 2. And then I'll break x1 into its individual components here. That's equivalent to x1. And that's equal to 0, right? And so you could write out the system of equations that is given by this equation that we have now, or you can just see intuitively that the vector x1 is simply going to be 1, 1, right? Because if we carry out this matrix multiplication, we're going to have this times this plus this times this, and if we throw both 1s in for x1 and x2, those will sum to 0, which is exactly what we want here. Okay, so our first eigenvector is 1, 1. Good. Now, for lambda 2, which we said was 3, we're going to do the same thing. A minus 3i times eigenvector 2, x2 equals the 0 vector. So now we're just going to subtract 3 across the main diagonal. So we're going to have all 2's in our original matrix. Again, I'm going to break down x2 into its individual components, and that's equal to 0 on both rows. Okay, So again, intuitively, this is a pretty friendly matrix here. We can see that the vector 1, -1, or any multiple of that, of course, is going to work, right? Because the way eigenvectors work, if we have this that's an eigenvector, right, every multiple of that vector is also valid because it remains along the same direction. Okay, so here we have our second eigenvector, which is 1, -1, again, or any multiple of that. And so now we can start to construct our solution, right? So we said that solutions are going to be vector valued functions that take this form, C1, eigenvector 1, which was 1, 1, e to the eigenvalue 1, which was 7, if I'm not mistaken. Sorry, 7t, plus C2 times eigenvector 2, e to this 3t. Sure. Okay. So the problem just wants us to find a linearly independent pair of solutions. So they essentially want y1 as a function of t, y2 as a function of t, z1 as a function of t, and z2 as a function of t. All right, and we have those, right, from this vector valued answer. Okay, so taking the first row as y, we can have y1 of t, right? Essentially what I'm doing is I'm just going to assume that constant's 1 here because a C1 of 1 is the simplest and least redundant way to express the answer. And so I'm just going to multiply the e to the 7t through that vector. So we get y1 as a function of t equals e to the 7t. Okay. And then y2 as a function of t is going to be the first row as well, but it's going to be the second term here. Again, I'm assuming C2 is 1. It could also be any constant, right? We said C2, right? So this can be a free constant. This is a free parameter. But I'm just going to say it's 1 for fun. So it's e to the 3t. And then to find Z1, we're just going to do the bottom columns. So that will be e to the 7t as well. And Z2, as a function of t, is negative e to the 3t. Again, you can use free constants in front of each solution for y and z. And additionally, you could also call these y and these z. It doesn't matter because, again, all we're looking for is a linearly independent pair of solutions. So that was just a brief, nice and easy example of how to find linearly independent solutions to a system of constant coefficient differential equations. So again, the process, right? Assemble our coefficient matrix, calculate the eigenvalues and eigenvectors of the matrix, and assemble our solution of the known form. So I hope this video was helpful, and thank you very much.